the calculus that you know is just part of it. Okay? We have a bigger, concept about the calculus. Okay? So let me put it this way. Single variable calculus. Okay? So there's only one variable in this calculus techniques. Okay? This is, the calculus that you mostly know. If we have a function, we have dx from x1 to x2. We have integration, right? That's the whole thing about differential calculus and integral calculus. Okay? What about multivariable then? This is single, means just one function of x, let's say, right? But what if, there are more variables than x? Then we can call it multivariable. Multivariable calculus. Okay, this is the calculus about multivariable. It's many variables. It's more than one, right? Okay, if I draw that, conceptually, that's what it is. X, Y, and this is function of x comma y, right? This is not z, but it's a function of x and y. Okay, that's the multivariable calculus. If we do the same thing, this is, dx, this is dy, and over the top of that, we have arbitrary surface or arbitrary shape. It's a function of f of xy, okay, the values of f of xy, and we have du, okay, dx dy is du, so we are kind of integrating over. So if we put, x1, x2, the lower and upper boundary for the integral, and y1 and y2 upper boundary for the, integral, then the integration is, I don't know, it's, and the under area, the volume, that's the integration, okay? So everything, this single variable really expands to the, multivariable, okay? Multidimensional concept, okay? So that's the pure definition of single variable and multivariable calculus. Okay? But we want for vector. So what's the relationship, with the vectors and this single multivariable calculus? We want vector calculus, right? What's the difference between single variable calculus with vector calculus or multivariable calculus to vector calculus? We have to exactly know that, all right? Because the vector, as you all know, this one has magnitude and what? Direction, right? This one, vector, came from interpreting physical phenomena, right? Physical happening. We wanted to, mathematically express the physical happenings with a vector. Vector. It's a new definition, right? Mathematical definition, and we want to know vector calculus. Okay. So we need to have differentiation with the vector and integration with the vector. Okay? Just for example. So vector calculus can have both single or multi-variable. Okay? So vector contains, single variable, multivariable, any variables. And we need calculus on that. Okay? For example, all right? Single variable, f of t. Let me put v. But it's a function of t, function of time. Okay? Like that. 2I plus t squared j plus 0.5 t k. Okay? Or 2t squared 0.5 t, or 2t squared 0.5 t. We have three, equivalent notations for the vectors. Okay? Right? Right. Let's try to draw it. Okay? So when time is 0, what is it? It's 2I, right? When time is 1, it's 2I plus j plus 0.5 k. Okay? And v of 2 is 2I plus 4j plus k. Why don't we draw it? On the plane, x, y, z. The first one, 2I, so it's I, j, k. The orthonormal vectors, right? They are linearly independent each other, right? Okay? And the v1 is 2I, so this is v of 0, okay? And v1 is 2 plus j, so it's 1, and 0.5 to the k, direction. So that's this. That's v of 1, right? And thirdly, 2 and 4 and z direction is 1. So it's this vector. So it's a v of 2. Okay? And this is a single variable vectors. This is one vector, but it's a function of t. So it changes as t changes, right? So it's like, from 0 to, this one changes like that. The v of t. Okay, that's single variable vector. All right? What about multivariable? This is single variable vector. Multivariable vector is like that. Okay? This is multivariable. You could have n variables, right? But it maintains the vector, the constant vector, consistently. All right? So we're gonna, in the upcoming lectures, we're gonna learn how to do the integration and differentiation of these vectors, because it's a function of multivariables. Okay? Before I keep moving on, let's define some terminologies. Okay, this is both magnitude plus direction. Okay, then scalar. This is a number, quantity, right? It has only magnitude. Okay? That's we have a special name, scalar. Okay, so we have some notations to write the, vectors. We have, this kind of vectors. We write this way, right? But in printed, But in printed, like in the book or in the printed material, we have this boldface for the vectors, right? Small alphabet letters with boldface. That's in printed form. Okay, and other forms, you could have A, B. Sometimes many people do that. Okay, but for these two, it's okay not to specify anything. But if you have very special names, you have to specify this is a vector or something like that, right? Before you use it, you have to specify this is a vector, right? Otherwise, people will get confused, right? So, but these ones, it's okay. You don't have to specify. I mean that, but still, people know that they are vectors. Okay. When you write a component, again to refresh you, component of a vector. Okay, this is. Let's say you have a vector from P to Q. Okay, this is P and that's Q, and that's your vector A. Okay, in space. Then this one will be projected to XY plane, right? And you have components on X A1, A2. And for Z, you have A3. Okay? And for Q, we have projection onto XY plane. Let's say here. Then you have no, not A1. Let's call it X1. This is Y1. This is C1. Okay? And this one is X2. This is Y2. And that is Z2. Sorry for that. Okay? It's not showing there. Then this is A1, and this is A2, and that is A3. Okay? In the component form. So if you write that, A1 is X2 minus X1, A2 is Y2 minus Y1, A3 is C2 minus C1. Okay? And the magnitude of the vector is this by the Pythagorean, right? Pythagorean. And another thing is, the position vector. Just to remind you, okay, refresh your memory. Position vector R of a point A, X, Y, Z. Okay? So in space, there's X, Y, Z. Okay? It's a vector. Then the R is from the origin to that point. That's R vector. The position vector. Okay? Addition is all easy, right? Addition. A vector plus B vector is A1 plus B1, A2 plus B2, A3 plus B3. Or you could write this way. B1, A2 plus B2, A3 plus B3. Okay? scalar multiplication. Multiplication. C times A vector is CA1, CA2, CA3. Okay? And we have unit vectors. Unit vectors IJK. We're going to have a lot of this, right? This is standard basis. Okay? So on X, Y, Z, R3 plane, I, J, K. I'm going to give you a kind of, problems. This is a building wall, or, building wall, okay? This is a building wall, okay? We want to put a advertising board, okay? We are viewing from the side, okay? This is a advertising board. And we want to attach that to the building, okay? And we want to have very simple support for that. This is a truss. Okay? We simply put two truss on that board and the wall. Okay? So, apparently we're going to have a weight of the board, okay? We call it P, okay, which is, we could put anything but 0 and, okay, I don't want to do it right now, okay? And what else in a force exists in this system? Since P, pulling down, there should be some resistive force, right? We call it U, let's say, right? But then this one has to support in this direction, right? And that's 45 degrees. Okay, find U and V. That's your, U and V. So if you want to get, U and V vector, what you have to do is this. The first step is you have to set up the coordinate, right? To be able to, calculate vectors, you have to set up the coordinate. And the natural selection would be, on the horizontal, it's X, right? And vertical, it's Y. Okay? So remember, you have to first set up the coordinates. And once you set up the coordinate, the vector can be represented on the coordinate, right? So it's U1, U2. Phi is Phi1, Phi2, right? So every vector has the components on each coordinate. Okay? Then we have trouble, right? We have 4 unknowns, right? Can you get the 4 unknowns, 4 conditions? Can you get 4 equations? No. Not likely, right? So we need to make it simplify to have better condition, right? Using the geometry, using the shape of the system or geometry of the system, we have to simplify it. We have to reduce the unknowns, right? Otherwise, we cannot solve it. We may not be able to solve it, right? So let's see. Okay, so U has only components on X direction, right? So Y direction is 0. That can simplify that, right? So that's 0 here. And we have only 1 unknown left, right? Secondly, V, we have to use the geometry, 45-degree relationship, right? So that's, if it's a 45, So x component and y component has to be the same, right? So we could do this, right? So we have only two unknowns. Two unknowns. Possibly you can get two equations, right? The next thing you have to use is what? It's in equilibrium. What is equilibrium? It doesn't move, okay? No movement and stable. That's the equilibrium point, equilibrium state or equilibrium system, okay? The system is very stable. It doesn't move at all. That's equilibrium state, okay? And we are using equilibrium. And equilibrium is net force, okay? Net force is 0. All the functions, if you add all the forces, that is 0. Okay? So we have three forces, right? The weight of the board and the supporting, force by the truss 1 and supporting force by the truss 2. Okay? So that you just add U plus V plus P, which is 0. Okay? And UVP is minus U, this is minus, let's put it that, plus V and V minus 1,000. Let's put in 1,000. Or P okay? So V is the weight and U is P. Okay? If we put, P to be 1,000 Newton, then it's 1,000 Newtons each.